Welcome to the second lecture of this week in EE404. In the last lecture, we have seen how to actually draw global phase portraits of nonlinear systems for some simple systems. And in this lecture, we are going to start with solving an example first. And if time permits, we are going to go into a new topic. Let us look at this example. So we are given a control system where the reference signal is equal to 0. And I have a nonlinearity here in the system. This nonlinearity is going to be a sine function. Okay, so it is 0 at 0. It is positive if x is larger than 0. And it is negative 1 then if x is smaller than 0. And I have double integrators here. Instead of integrator, I can write 1 over s. 1 over s. This is going to be the signal x1. And I have the signal x2 defined like this here. And I will call this signal as tau. I will tell you why it is called tau here. And we would like to draw the phase portrait of the system. Draw the phase portrait of the system. So this is a satellite control system. So let me explain why it is a satellite control system example. So here is the plant that we would like to control. So it starts from tau and it goes to x1. x1 is like an angle here. So although we call it x, it is actually an angle. And we know that the system from tau to x1 is nothing but 1 over s squared. And here, let me say instead of x1, let me say theta 1 here. So if I have a system given like this with transfer function 1 over s squared, what are the equations? I have theta of s over tau of s is equal to 1 over s squared. And that means that I have s squared theta of s is equal to tau of s. All right? So here I call theta, the variable here, theta 1. So this is theta 1 of s, and I have theta 1 of s. So if I go into time domain, I would write this as theta 1 double dot is equal to tau. Okay? So you see that this is just an inertia which doesn't have any friction. All right? So you can think about this equation as j times theta 1 double dot is equal to tau minus b theta 1 dot. Here we select j is equal to 1 and b is equal to 0. Therefore, then this system turns into this equation turns into this simple equation here. This is a simple mathematical model of a satellite in space. So we have a mass that can rotate here. It's the body of the satellite, and we have something like this. And we would like to control the angle of the satellite. Let us say that this is r equals to 0, and let us say that this is our theta. Okay? And suppose that we would like to bring theta to 0. Okay? So, and here I assume that the inertia is equal to 1. Of course, there can be some scalings here. If the inertia of the satellite is not equal to 1, this is just a simplification. And we assume that there is no friction in space. That means that we're going to have just a simple double integrator. So the double integration of the torque applied onto the satellite body is going to be theta 1. All right? So we would like to bring the angle of the satellite, theta 1, that is theta 1, to 0. Okay, so we would like to bring it to the reference 0. And in this feedback loop, how do we want to achieve it? So you see that here, we are actually here defining a feedback loop here. The torque that is applied onto the inertia is given by a sine function. We first calculate an error, and if the error is positive, we apply a constant torque independent of the magnitude of the error. So this is error here. Independent of the magnitude of the error, we apply always a constant torque 1 here to the inertia. Okay? Suppose that theta is positive. In that case, we just apply a torque that is whose direction it can be defined here in order to bring the angle of the satellite to 0. And if the error is negative, in that case we just apply a negative torque. Okay? Onto the body of the satellite system. And we would like to, at the end, we would like to achieve the control of the satellite, and we would like to bring it to the reference theta 1 equals to 0. Okay? So now let us try to see if this type of system would be able to actually achieve such an aim. All right? In order to be able to investigate this, we are first going to define a mathematical model of this system. So here, I can go back to my x1 and x2 variables, and then I can think about the original system. So here, in order to be able to define the state space model, I will define my state as x1 and x2 signals here. x1 signal here is this. It is the angular position of the satellite, and I have x2 is given as this variable in the block diagram. So now let us try to obtain the mathematical model. But before defining the mathematical model, I can define what this function is. So this is the sine function, okay? So here, this tau is nothing but sine of the error signal, okay? And this is defined as, in this example, as it is 1 if error is positive, it is 0 if error is 0, and it is -1 if error is negative. Okay? So in order to be able to obtain the mathematical model here, I need to obtain what x dot and x1 dot and x2 dot in terms of x1 and x2. So here let us look at this picture. If I have an integrator, if I have 1 over s, and if it is output is the signal x, then what can I say about its input? If the output of an integrator is x, then the input, its input is going to be x dot. Okay? So in this block diagram, I can actually use this type of methodology to obtain my state space representation here. So I see here that x1 is the output of the integrator with the input x2. That means that x2 is x1 dot, okay? Or x1 dot is equal to x2. That is going to be our first equation, okay? x1 dot is equal to x2. And similarly, I have x2 dot is going to be tau. x2 dot is going to be tau, but tau is nothing but sine E. Sine. And E is the reference, which is equal to 0, 0 minus x1. So I have minus x1 here. All right. So this is our mathematical model for this example, and we would like to obtain the phase plane trajectories of this system. Here, before I continue, I will just here make a small modification. x1 that is equal to x2. I see here that the sine function is an odd function. So if I substitute minus a variable inside sine, then that minus can be taken outside. So here, instead of x2 that is equal to sine minus x1, I can write minus sine of x1. Okay? It is the same mathematical model here. Now I'm actually ready to be able to obtain the phase plane trajectories of the system. These type of systems in control systems are called variable structure systems. Variable structure systems. What does it mean? It means that depending on some state variables, the structure of the system can change. Okay? For example, this is not a variable structure system. x1 that is equal to x2, x2 that is equal to x1 squared. So depending on the sign of the state variable, the structure of the system does not change. But the system that I have written here, if x1 is positive, I see that x2 that is minus 1, and if x1 is negative, then I see that x2 that is equal to plus 1. Okay? So you see that the structure of the system, so the equations of the system are changing based on sign of x1. Okay? So these are called variable structure systems, and there is a separate literature for these type of nonlinear systems. And sometimes variable structure systems are called switching systems. And it is clear that this sine function actually switches the dynamics of the system depending on the value of some state variables. So now, what type of equations are we going to have? So our equations are going to be dependent on x1. There are three cases. x1 is positive, and x1 is 0, and x1 is negative. Depending on these inequalities or equalities, the equations of the system are going to change. x1 that is equal to x2 is always the same in all equations. And the second equations are going to change. x2 dot is equal to, if x1 is positive, then I would have minus 1 here. If x1 is 0, x2 dot is equal to 0. And if I have negative x1, then I have x2 dot is equal to 1. Okay? So now that for these systems, individual systems, the system switches between these dynamic systems. And for these systems, I can try to find the state space trajectories, phase plane trajectories. So let us use our theory. dx1 over dx2 is equal to minus x2. And in this case, I can actually write this equation as dx1 is equal to minus x2 dx2, okay? And I can integrate both sides, which is going to give me x1 is equal to minus x2 squared over 2 plus c, all right? And this is going to be the trajectories in this region, x1 equals to 0. And I can actually draw this state space here like this. This is x1, x2, and you see that I have three regions. This region is just a line, x1 equals to 0, it's x2 axis. x1 positive, this dynamic equation is going to be valid here on this part of the state space. And when x1 is smaller than 0, these dynamics here would be valid on the left-hand side. Okay? So here I can actually write dx2 over dx1 is equal to 0. That means x2 is equal to constant. But we will actually see that this part is not really going to be important, because it is only going to correspond to this single line, and it's only going to be a single point which would use this dynamic. So this part is not really going to be important. And this is dx1 over dx2 is equal to x2. And I can write dx1 is equal to x2 dx2. And this is integrating x1 equals to x2 squared over 2 plus c. Okay? So now I can try to draw these phase plane trajectories. So here I have x1 is equal to a minus x2 squared over 2. So we know how a parabola looks like. So this is my x1, this is x2. This is a parabola which is showing x1 equals to x2 squared. x2 squared over 2 is going to be like this. And I have negative x2 squared over 2, so these things would be looking like this. So these equations would be looking like reverse parabolas, and I will still shift them to the right. Okay, why is that? Because of this c here. C plus minus x2 squared over 2. So here, for this case, x1 is always positive, and x2 squared over 2 is always non-negative. Take this term to the left-hand side. You see that c is equal to x1 plus x2 squared over 2. So here I see that x1 is always positive and x2 squared over 2 is always non-negative, meaning that c should be always positive for this case. Okay? Because of the region where this dynamics is valid, it enforces that this c, it needs to be positive. Okay? Meaning that this reverse parabola is always going to shift to the right here for positive c. When I look at this parabola like this, I will add a positive constant to it. And therefore, the trajectories would be looking like this. So here, these trajectories on this part of the state space, therefore, they would always be looking like this. Some reverse parabolas, and these C's would depend on the initial conditions, but all of the trajectories would be looking like this. All right? And what about the direction of motion on these curves? On these curves, I know that x2 dot is equal to always negative 1, meaning that x2 should always decrease on those curves. All right? So I see here that x2 should always decrease, meaning that the direction of motion on these curves should be like this. So here, let me come to here. x1 equals to, this is for this case, x1 equals to x2 squared over 2 plus c. In this case, again look at the sign of this constant c. Take x2 squared over 2 to the other side, you get x1 minus x2 squared over 2 is equal to c. x1 is always negative in this region, and x2 squared over 2 is always non-positive, meaning that c should always be negative here for this case. Okay? And that means that, and I know that here, these parabola, x1 equals to x2 squared over 2, they would be looking like this. This is x1, this is x2. x1 equals to x2 squared over 2 would be looking like this. And if c is negative, I will subtract c. So they would always be looking like this. So the parabola on the other side, they would be looking like this. All right? Of course, they should be symmetric with respect to the x1 axis. And what about the direction of motion? x2 should always increase on those curves. So the direction of motion should be just like this. And actually you can also gather that information from the continuity. If you know these directions, you would know these. Then what about this third case? x2 equals to, what about this third case? x2 dot is equal to 0. So this dynamics is only valid when x1 is equal to 0, okay? So this third dynamics here is only valid on this line, okay? Suppose that we are somewhere here when x2 is positive, okay? If the trajectory ends up here on this line, then this dynamics becomes valid because x1 is equal to 0 there, okay? Then this dynamics tells me that x2 is going to remain constant at this value, but what is going to happen to x1? x1 dot is going to be equal to x2. So if this value is 3, then x2 is going to remain at 3 as long as x1 is equal to 0, and x1 dot is going to be equal to 3, meaning that x1 is immediately going to increase because x1 dot is positive. So if the system arrives here on this axis, it is immediately going to leave this point because x1 dot is going to be equal to x2, and that means that x1 dot is going to be positive and x1 is going to continue to increase, okay? So this point really is not very important because the system never stays there. The system immediately leaves that point, and this dynamics then becomes invalid in that case, okay? So this x2 equals to constant dynamics, it is never seen in this case, because even if x1 comes to the value 0, it immediately leaves that value because x1 dot is equal to x2, okay? And then x2 being positive or negative would immediately make the system leave x2 axis, okay? There is only one exception to this, and it is this point. If x1 equals to 0, I have this dynamics, and what happens if x2 is equal to 0 as well? x1 dot becomes 0 as well, so x1 remains constant. So then what happens? Then this dynamics is valid. x2 is going to remain at a constant value, and furthermore, and that constant value is 0, and x1 is going to remain at a constant value, and that constant value is 0. But what does that mean? If the system reaches here, then it's going to remain there. What is the meaning of this? It means that this system has an equilibrium point at the origin. Okay? And actually that is where we are trying to bring the satellite angle to. We want the satellite angle to remain at 0 with 0 velocity, meaning that we need to come to the state space if we want to achieve, we need to come to the origin of the state space if we would like to achieve our control A. So this actually completes our trajectories, and you see how much we achieve with this type of control system here. You see that with this type of control system, if the angle of the satellite, if it is at some non-zero point, then with this type of control, it's going to oscillate forever. Okay? It is never going to be able to settle at anywhere, and it's going to oscillate with this simple feedback loop. Okay? So this is not really a very good control strategy, maybe. So that is why we need to modify this system. Okay? So this really doesn't achieve, this control system really doesn't achieve our control aims, meaning that we need to change our control strategy. Here, our controller is just this one. Okay? So this type of positive torque, or negative, maximum positive torque or maximum negative torque of strategy in control theory is called bang-bang control. Okay? So you either apply the maximum positive torque or force, or you apply maximum or negative minimum torque. Why is that such a control strategy? The answer to this question, the answer to this question is, so why not a proportional controller here? The answer to this question lies actually in the hardware that is used to control the satellite. Okay, in the satellite, we have some thrusters. They are called thrusters. So and here. Somehow, for this example, we assume that they can either apply maximum torque on that direction, or they can apply maximum torque in the other direction. Okay, so there are no degrees of control in that hardware. Okay, so it can either apply a maximum torque in one direction, or it can apply the maximum torque in the other direction. Actually, there is no positive, negative there either. Okay? Here, there might be just some rotation. And the thruster can only apply a torque in one direction, and you can change its direction in order to be able to apply torque in the maximum torque in the other direction. Okay? So it can be just that. You have a single thruster, and you can either turn that thruster in that direction or in that direction, and that's going to give you either the maximum torque without any degree or any knob there. So you can just get the maximum torque in that direction or in that direction, and that is the only thing that you can do here. Okay? So this type of switching might come from the hardware of the system, actually, hardware limitations of the system. So this is not actually in that case, it's not actually a controller anymore. It is actually a nonlinearity that is modeling the limitations of the hardware that we are using in our control. Okay? So we see that this controller really does not look good, and it causes the satellite to oscillate forever when we try to bring it to an equilibrium at the origin. Okay? So what happens is that if the pendulum has non-zero angle, at the end, if I use this control strategy, it always oscillates like this in space. Okay? It never achieves the equilibrium. It never settles at the desired angle. So how do we modify this? So now I'm going to modify the system just a little bit, okay? By adding another type of controller into the picture. The switching would still remain because it is modeling the limitations of the control hardware here, but I'm going to add just another block here, okay? And this block is going to have the transfer function s+1. Okay? So here I have my sine function still due to the hardware. And sometimes instead of integrators, people would put here, instead of 1 over s, people would put integrator sines here. So this is our new system. Okay? Now I would like to obtain the mathematical model of this new system, and I would like to obtain the phase plane trajectories of this new system. I have still the same variables, x1, x2, and I have tau here, I have the error, and now I have added this new block here, okay? This new block is S plus 1. Can you tell me what type of controller that block S plus 1 is? It contains an S and a constant. So we know that S is derivative and 1 is just a proportionality constant, meaning that this is a PD controller, okay? So now we would like to obtain the mathematical model of the system with the PD controller. So I have still the reference equal to 0. And let us look at the signals here. Instead of this error signal, I can actually write minus x1, okay? Because this is r minus x1 is minus x1. And what is the signal here? It is going, I will take the derivative of minus x1. It is minus x1 dot, plus I will take the variable itself, minus x1, okay? So s plus 1, if minus x1 passes from the system s plus 1, I take its derivative and I take itself and then I sum it, all right? So this is E dot plus E, and here E is equal to minus x1, okay? So I have this signal here. Now I can write the mathematical model. x1 dot is equal to still x2 here. This is nothing but the physics. The derivative of the position is the velocity that tells us this. So x2 is angular velocity here, and x2 dot is equal to tau. Tau is sine of the input variable here, and the input variable of the sine is minus x1 dot minus x1 minus x1. So is this a valid state space system, or is this a valid state space representation? Clearly it is not. A state space representation should look like this. x1 dot is equal to f1 x1 x2, and x2 dot is equal to f2 x1 x2. Okay? That means that the only derivatives should appear in a state space system on the left-hand side. On the right-hand side, there shouldn't be any derivatives. Okay? So that means that this x1 dot here is not really good. This makes this state space representation useless. This is not a valid state space representation. So what am I going to use instead of x1 dot here? Look at the previous equation. x1 dot is equal to x2. That means that I can remove here this derivative here, and I can write here x2. Okay? Now this is a valid state space representation, because in the right hand side I don't see any derivatives as it needs to be. Okay? So now I can actually do the manipulation that I did before there, and that is going to give me x1 dot is equal to x2, and sine function is an odd function, meaning that sine minus e is equal to minus sine e for any e. That means that I can take these minus signs to the outside. x2 dot is equal to sine minus sine is equal to minus sine. I have x1 plus x2. Okay? So you see that the only thing that has changed in the system is this argument of the sine function. So in the earlier case, I had only x1 in the argument, and now I have x1 plus x2. So here we are going to see that when x1 plus x2 is positive, I would have this dynamics. When x1 plus x2 is negative, then I would have this dynamics, okay? So it is only the switching boundaries or the switching regions which have changed in this new system. So by adding a PD controller, I have changed this switching line. In the earlier case, the switching line was x1 equals to 0, the line x1 equals to 0, okay, which is the x2 axis. But now in this new system, the switching line is going to be x1 plus x2 equals to 0. So in the state space, my new dynamics is going to switch at some place other than the x1 axis, all right? So now let me draw the state space once more. So I have x1, x2 here. Now my switching boundary is going to be the line x1 plus x2 is equal to 0. So our switching line is going to be x2 equals to minus x1 line. Okay? Now which dynamics is valid where? So I have, if x1 plus x2 is positive, then this value is going to be 1, and there is a minus 1 here, so I would have minus 1. So when x2 is larger than or equal to minus x1, then I would have this dynamics, okay? So when x2 is larger than or equal to x1, which means this part, not this part. In this part, I would have this dynamics, and if in the other part, I'm going to have this dynamics, okay? So now these conditions here have changed. So I can erase these inequalities, and this is valid when x2 is larger than minus x1, and there is no equality here. When this is true when x2 is minus x1, and this is true when x2 is smaller than minus x1. Okay? But the equations would remain the same because the sine function is either 1 or minus 1. So these equations will not change, and these equations, these trajectory equations would not change. Okay? So as a result, I can actually draw my trajectories as before. So I would have, on this part, I would have this type of parabolas, and on this part, I would have this type of parabolas. Okay? Just like this. Here, I have taken this switching line, and I have rotated it to x1 is equal to minus x2 line. Okay? So now let us start. Suppose that we start somewhere here. It really doesn't matter, but it's going to be good if we start somewhere here. Okay? So since we are to the right of this boundary, this dynamics is going to be valid, and so we are going to have parabolas which would rotate like this. So at this point, we are going to have a parabola. It's going to pass this axis, and then it's going to come back like this. Okay? So the direction is still the same. So now as soon as we hit this point, of course this dynamics is going to be valid, but we know that this is only going to be a single point, and we are going to immediately cross this line. Okay? Just as we did here. Okay? And then, as soon as we cross this line, the other dynamics is going to start to become valid. Okay? And we know that dynamics is going to give another parabola. Okay? But this parabola is going to be going towards this axis, it's going to cross there, and it's going to come to the other side symmetrically. Okay? So here I'm always drawing symmetric parabolas, but you see that when I start here and when I draw a parabola symmetrically, one of the parabolas is cut here, okay? Much earlier than it is its originating point, okay? If the dynamics didn't change, it would have continued until here, the symmetric part of this point. But it is never able to come to the symmetric part here, because here is the switching boundary, so the dynamics immediately switch as it crosses this point. Okay? And then the other dynamics start to become valid. Similarly, when I try to draw a parabola here, it's going to be symmetric. But when it is going towards its symmetric point, you see that it is cut here because the dynamics is again going to change to the other parabola. Okay? But you see that in each parabola, we are actually ending at some point. We are switching at some point which is closer to the origin than the original starting point. So we're going to continue like this, and we're going to switch here again, and switch and switch and switch. Okay, and then we are going to end up exactly at the equilibrium point of the system. Okay? So we see here that the addition of this PD controller here, it changes the switching boundary of the system, and as soon as we switch the boundary of the switching, we see that we achieve a convergence to the equilibrium point. Okay? Of course, sometimes when we try to put another controller here, we might make some mistakes. So here we see that if I put this PD controller there, I could achieve a convergence to the equilibrium point. What would happen if I started somewhere here? It would be the same. It really doesn't matter. So wherever we start now, we're going to end up at the origin. Okay? So sometimes, of course, instead of using this correct PD controller, I can change the PD controller. I can make this 2s plus 1. I don't think much is going to change. Again, the switching boundary is going to change. That line is going to change. But I would still think that we are going to be able to converge. But what happens if I make this sign of this as negative? So actually, I will not do it in the class. So I'm asking you to do it as an exercise. So try to model this system when you change the PD controller into -s plus 1, and try to obtain the dynamics and try to show what happens in the state space of the system. Do we still have a convergence, or is this going to be a mistake, putting a minus sign there? Sometimes feedback can make things much worse than actually the case without feedback. Okay? So my aim in that exercise is to show you that if you put a minus sign here, the things are really going to go bad. They are going to go worse than the case without actually the feedback. Okay? So this completes this interesting example. Now I'm going to start with a new topic. So we see that in the nonlinear systems, these oscillations, the oscillatory behavior, really appears a lot. And we are going to see that nonlinear systems can sometimes show a very specific oscillatory behavior. And we are going to call that type of behavior as a limit cycle. So let us say limit cycles. I'm first going to define what a limit cycle is, and then we're going to talk about that definition. An isolated periodic trajectory, in other words, solution of the system x dot is equal to f of x is called a limit cycle. So in this definition, the most important thing that you need to pay attention to is this adjective. It is isolated. So we see that linear systems have periodic trajectories. Nonlinear systems can have periodic trajectories, but not all periodic trajectories are actually limit cycles. Okay? They are not called limit cycles if they are not isolated. So remember, we have defined in the past, at the beginning of the course, an equilibrium point, and we have classified them as isolated or non-isolated. So remember, when we have an equilibrium point, and when we look at its close neighborhoods, it's a small neighborhood around it, if we can find a neighborhood around that equilibrium point that doesn't contain another equilibrium point, then we would call that equilibrium point an isolated equilibrium point of the nonlinear system. Okay? So a similar concept here is considered about the periodic trajectories. Okay? So here, if in the state space, if we have a periodic trajectory of the nonlinear system given like this, we are going to look at it is epsilon neighborhood around it. Okay? We are going to look at an epsilon neighborhood around that periodic solution. And we are going to check if there is another periodic solution in that epsilon neighborhood around that periodic solution other than the original periodic solution. Okay? So we will look at an epsilon neighborhood around this periodic trajectory, and we will check if there exists another periodic trajectory than this original periodic trajectory in that small neighborhood. If there is no other periodic trajectory in that neighborhood than this periodic trajectory, then we are going to call that periodic trajectory an isolated periodic trajectory. Okay? On the other hand, if however small epsilon neighborhood we look at, we would always find another periodic trajectory in that neighborhood, then we will call the original periodic trajectory a non-isolated periodic trajectory. Okay? So that is the meaning of isolatedness in that definition. So a periodic trajectory is not always a limit cycle. We can call a periodic trajectory a limit cycle if and only if it is isolated. Okay? So now let us look at the following example. This is going to be a linear system, and I would have x1 that is equal to x2, x2 that is equal to minus x1. It's a very, very simple example. Let us obtain the trajectories of this system. So I would write here dx1 over dx2, that is equal to minus x2 over x1. I take here x1 dx1, and minus x2 dx2, integrate both sides. x1 square over 2 is equal to minus x2 square over 2 plus c. Take minus x2 square over 2 to the other side. Multiply by 2 and call 2c as c again, and you get the equations for the trajectories of the system. And you see that these are actually simple circles around the origin with different radii that depend on the initial condition. Okay? So we have trajectories like this. What about the rotation direction, clockwise or counterclockwise? In that case, I would just look at this point. In that case, then x1 is positive and x2 is 0. So x1 that is 0, x2 that is equal to, let us say, a negative quantity. That means that this is going to rotate like this. So here, it is really important that you understand what happens when I change C here. So let me say that this is, so suppose that my initial condition here, x1 0 is equal to 1 0, okay? So sorry, this initial condition. The first initial condition that I consider is 1 0. That would make c equals to 0, c equals to 1 here, and the trajectory would be looking like this. A circle, clockwise rotation, and my initial condition would be here. Now I'm asking, so this is a periodic trajectory. Clearly, this is periodic, okay? But is this periodic trajectory an isolated periodic trajectory, okay? For that, I need to look at an epsilon neighborhood around this periodic trajectory. I am defining an epsilon neighborhood of the state space around this periodic trajectory. Let us say that this point here is 1 plus epsilon, and this point is 1 minus epsilon. Okay? I can make epsilon as small as possible. Okay? I can take it arbitrarily small. Now the question is, can we find another periodic trajectory in this epsilon neighborhood? Can we always find another periodic trajectory in this epsilon neighborhood other than the original periodic trajectory? And the answer to this question is actually yes. Now consider the following initial condition. x02 is 1 plus epsilon over 2, okay? And 0, all right? Then I would start a periodic trajectory right in the middle of 1 and 1 plus epsilon, okay? The initial condition would be like this. So then C is going to be equal to 1 plus epsilon over 2. Then that is going to be giving me just another circle, okay? Just another circle here, which would be in the same neighborhood as the original circle, okay? And this is true however small epsilon I choose here. Of course, epsilon has to be positive, but however small epsilon I choose, however small I make that neighborhood, I will always be able to find another periodic trajectory in that neighborhood, and that means that this original periodic trajectories of the system is not an isolated periodic trajectory, okay? So I can take any periodic trajectory of this linear system and I can look at its any epsilon neighborhood, and then I can always find another periodic trajectory in the same neighborhood as the original trajectory. Okay? So here I can say that, yes, this system has periodic trajectories, but none of those periodic trajectories are isolated. Therefore, this system, it doesn't have any limit cycles. Okay? Because I can only call a periodic trajectory a limit cycle if it is isolated, if and only if it is isolated. If all trajectories of this system are not isolated, I can show it. That means that no limit cycles. Okay? But you see that all of the trajectories of this system are periodic. There are infinite number of periodic trajectories of the system, but none of them are actually limit cycles. So this linear system really does not have any limit cycles, although all of its trajectories are actually periodic trajectories. Okay? So this is actually true whatever linear system that you select. Okay? Whatever linear system you select, and suppose that you have a periodic trajectory of that system, by modifying the initial condition of a linear system, you can always get arbitrary closed periodic trajectories of the same system by modifying the initial condition. Okay? So this type of result is actually true for all linear systems. Whatever linear system you choose, it cannot have any limit cycles because of the scaling property. If I scale the initial condition the infinitesimally, then the periodic trajectory is scaled infinitesimally, meaning that I would always be able to find another periodic trajectory in the vicinity of an original periodic trajectory. Meaning that if a linear system has a periodic trajectory, it can never be isolated. Meaning that the linear systems cannot have limit cycles. So let us write this as a remark. When linear systems have periodic trajectories, they are not isolated. Those periodic trajectories are not isolated. Hence, linear systems do not have any limit cycles. Okay? We can only call isolated periodic trajectories as limit cycles. So now let us try to see what can happen in a nonlinear system. So I'm going to modify this system a little bit by adding some nonlinearities into it. The new example looks like this. x1 dot is equal to x2 plus alpha x1, 1 minus x1 square minus x2 square, and x2 dot is equal to minus x1 plus alpha x2, 1 minus x1 square minus x2 square. We are going to investigate the trajectories of this system, and this is a nonlinear system, and we are going to look at if it has a periodic trajectory or not. And once we find a periodic trajectory, we are going to check if that periodic trajectory is isolated or not. Okay? If it is isolated, then we can say that this system has a limit cycle. Okay? Sometimes nonlinear systems can also have non-isolated periodic trajectories. Okay? So actually, So here we have an implication. This is always, so if I have a linear system, then I would always have non-isolated periodic trajectories. I have an implication like this. If I have a linear system, then all periodic trajectories are non-isolated. Okay? So what can I say if I have a nonlinear system? Then all trajectories are all periodic trajectories are isolated. Can I say that? So this implication really does not mean that. So this is P implies Q, and I know that the equivalent statement to this is that Q complement implies P complement. Okay? And Q complement is if some periodic trajectories are isolated, then that system should be a nonlinear system. Okay? But if the system is nonlinear, then you cannot say that its trajectories are isolated or non-isolated. They can be isolated or they might not be isolated. You don't know. Okay? So the equivalent statement to this statement would be if there are isolated periodic trajectories, we need to have a nonlinear system. That is the correct equivalent. But if you have a nonlinear system, you cannot say. So this is not equivalent to P complement implies Q complement. This is not equivalent. Okay? So now let us try to look at this system. Let us try to go back to that system. So it is clear that we will not be able to see the global trajectories of that system with some analysis. And by analysis, I'm meaning a coordinate change. And as soon as you look at this system, I really want you to be able to see what type of coordinate change that you can apply to that system to be able to analyze it in an easy way. Okay? Once you look at that system, can you see what type of coordinate change you can apply on that system to make the analysis easy? So here, these x1 square plus x2 square, it would show us that it is actually the radius variable, and that actually gives us a hint that if I go into polar coordinates, then the system might look in an easier with easier equations, then that would give us an idea about the trajectories of the system. So let us say that x1 is equal to r cosine theta, x2 is equal to r sine theta. Until now I have done this a few times now, so I will not do it by a lot of explanations. So I will calculate x1 dot, it is r dot cosine theta minus r sine theta dot is equal to x1 dot here is given as x2 r sine theta plus alpha, and I have here x1 r cosine theta, and I would have here 1 minus r square. And the second equation is going to be obtained by taking the derivative of this one. R dot sine theta plus r cosine theta dot is equal to minus r cosine theta plus alpha r sine theta 1 minus r square. So now let us try to extract the equation for r. Multiply the first equation by cosine theta, multiply the second equation by sine theta, and sum. Then that is going to give me r dot is equal to, these terms are going to cancel, but these terms are not. Then that is going to be alpha and r 1 minus r square. And if I do the same thing for theta, multiply the first equation by minus sine theta, multiply the second equation by cosine theta, and sum, then that is going to give you r theta dot is equal to, I have minus r. Okay? If I assume that r is not equal to 0, then that is going to tell me, if r is not equal to 0, that's going to tell me theta dot is equal to minus 1. Okay? So now we are going to try to look at the trajectories of this system. The equations are r dot is equal to r and 1 minus r square, and I have also an alpha variable here, and theta dot is equal to minus 1. So we see that we are going to always have a rotation. Theta dot is equal to minus 1. It tells us this, and that rotation is going to be clockwise rotation, just as the original linear system, which was this. Okay? So we have clockwise rotation. And here I see something interesting. This r is always positive, and except when we are at the origin. So let us consider the case when actually, which one I should consider first? Let us consider positive alpha case. Okay? In the case of positive alpha, then I would have, for example, r dot is equal to, let us say alpha is equal to 1, r 1 minus r square, and theta dot is equal to minus 1. So I see something interesting. When r is equal to 1, r dot becomes 0. Okay? So the radius does not change when actually r is equal to 1. Okay? So we see that this system has a periodic trajectory when r is equal to 1, and that periodic trajectory has the radius 1, and it's like a perfect circle, just like the original linear system. Now I can consider what happens inside this period, when the state is inside this periodic trajectory, and what happens when the state is outside this periodic trajectory. Okay? So the aim here is to check if there exists another periodic trajectory infinitesimally close to this original periodic trajectory inside this circle or outside this circle. Okay? So suppose that r is just slightly smaller than the original r, which is equal to 1. Okay? Suppose that r0 is equal to 1 minus epsilon. Okay? So we start the initial radius with an infinitesimally close value to 1 from below. Okay? So I start the radius infinitesimally. This doesn't look like infinitesimally close, but assume that this is infinitesimally close. Okay? So now I know that there is a rotation, but if r is if the initial r is infinitesimally smaller than 1, then what happens to this 1 minus r square? It is no longer equal to 0. And that means that r cannot remain constant. When I started at this initial condition, r cannot remain constant because r is not 0 and 1 minus r squared is not 0 either. That means that r dot is going to be something non-zero. What about its sign? If r0 is 1 minus epsilon, then this is going to be positive. 1 minus r squared is positive. R is positive, meaning that r dot is going to be positive. So what this means is that as soon as I start the system here, the rotation is going to continue, but since r dot is positive, r is going to get larger and larger. Okay? So we are going to approach to the original periodic trajectory. R is going to reach the value 1 at some time, and then the periodic oscillation is going to continue. Okay? So you see that I started the system infinitesimally close to this periodic trajectory, and I didn't get another periodic trajectory. What happened instead? Instead, this trajectory that I started converged back to the original periodic trajectory. Okay? So except for the equilibrium point, which is at the origin, wherever I start my system, the trajectories started inside this circle, they will always converge back to this periodic trajectory here. Okay? So inside the original circle here, I will never be able to find another periodic trajectory. Okay? There is nothing like this. There is no rotation like this. All trajectories started inside this periodic trajectory would always converge back to this original periodic trajectory because of the radius dynamics here. Okay? So I can say that there is no other periodic trajectory inside this periodic trajectory. Okay? What happens if I look at the outside? If I start the system somewhere infinitesimally close to this periodic trajectory, but with larger radius than 1. Instead of 1 minus epsilon, I can look at 1 plus epsilon. In that case, the rotation is still going to continue, but 1 minus r squared is going to be negative. That means that r dot is going to be negative, so there is going to be a convergence back to the original periodic trajectory here. If I start the system outside the periodic trajectory, all trajectories will converge back to the original periodic trajectory. I'm saying too much periodic trajectory. Okay, so outside there cannot be other periodic trajectories either, let alone infinitesimally close one. Okay? We only have to make sure that there are no infinitesimally close periodic trajectories here, and we could show that outside there are no periodic trajectories, inside there are no periodic trajectories, let alone infinitesimally close ones. Okay? So this periodic trajectory that we found originally, r equals to 1, is a periodic trajectory of this nonlinear system, and it is isolated. Okay? Is an isolated periodic trajectory of the system, meaning that r equals to 1 is a limit cycle. Okay? And when we actually locate, or when we discover limit cycles for some system, we are going to talk about its stability as well. Okay? When we discover limit cycles for a system, we are also going to be talking about the stability of those limit cycles. Remember, we called an equilibrium point of the system stable if I start the system very close around that equilibrium point, then convergence happens back to the equilibrium point. Okay? So here we're going to apply a similar idea. When I start the system very close to this limit cycle, if there is convergence back to the limit cycle, I will call that limit cycle a stable limit cycle. Okay? So for an equilibrium point, we call it stable if trajectories started in a neighborhood around it would always converge back to the equilibrium point. Okay? And here, we are going to call a limit cycle, a stable limit cycle, if trajectories started infinitesimally close to that limit cycle would always converge to the limit cycle. Okay? And in this case, this is r equals to 1 is a stable limit cycle. Okay? So then what does an unstable limit cycle would look like? Second case, alpha is smaller than 0. Okay? In that case, I have r dot is equal to, let us say alpha equals to -1, minus r, 1 minus r square here. Theta dot is equal to -1 still. So you see that r equals to 1 is still a periodic trajectory. Okay? And I have clockwise rotation like this. r equals to 1 is still a periodic trajectory, but what happens if r is smaller than 1? If r is smaller than 1, this is positive, but there is a -1 here now. So then r dot is going to be negative. So when we start the trajectories inside this r equals to 1 circle, then the trajectories are going to have r dot is equal to a negative quantity, meaning that the trajectories are going to get away from the equilibrium point and actually, get away from the limit cycle, and actually you can show that they are going to converge to the equilibrium point. Okay? Because r dot is always going to be negative inside the limit cycle, and you see that the trajectory, since r dot is always going to get smaller and smaller, we're going to have a convergence back to the equilibrium point, which is at the origin. What happens when we start the trajectories outside the limit cycle? In that case, 1 minus r squared is negative, and there is also a negative sign here, meaning that r dot is going to be positive. So that means that r is going to get larger and larger, meaning that the trajectories are going to get away from the limit cycle again. All right? So that means that any trajectory started infinitesimally close to this limit cycle is going to get away from the limit cycle. Meaning that, and it is sufficient that there exists only a single trajectory which is started infinitesimally close to that limit cycle that would diverge for us to actually call that limit cycle an unstable limit cycle. Okay? So in this case, r equals to 1 is an unstable limit cycle. And it is again a limit cycle. Why is that? Because I cannot find any other periodic trajectory infinitesimally close to that limit cycle, inside or outside. Okay? Let us look at the third case, 3. Alpha equals to 0. In this case, I would have the equations r dot is equal to 0 and theta dot is equal to -1. So in this case, whatever radius I select, it's going to remain constant. Okay? So I would have infinitely many circles for different initial conditions. So now what do I say? The system has infinitely many limit cycles? This is a tricky question. If you say that the system has infinitely many limit cycles, then you are definitely wrong. Because here you see that there are infinitely many periodic trajectories, but none of them are isolated. Okay? So in this case, we don't have any limit cycles. No limit cycles. Why is that? When alpha is equal to 0, the system turns into a linear system. Okay? So if alpha is equal to 0, I have a linear system. So any periodic trajectory would not be isolated, meaning that there are no limit cycles. So we have defined a limit cycle, and we have defined a stable limit cycle, an unstable limit cycle. There is also something called, which is sometimes used, a semi-stable or semi-stable limit cycle. Okay? And it is actually an unstable type of limit cycle because there are diverging trajectories from it. So if you would like to classify the limit cycles into two, stable and unstable, then a semi-stable limit cycle is an unstable limit cycle because there are always unstable trajectories diverging away from it. All right? If all trajectories around a limit cycle would converge back to the limit cycle, we call it a stable limit cycle. If there exists some trajectories, or at least one trajectory, which would diverge away from that limit cycle, we call that limit cycle an unstable limit cycle. A semi-stable limit cycle would look like this. Suppose that I have r equals to 1. Suppose that the trajectories inside are diverging away from the limit cycle, okay? And suppose the trajectories outside, they are converging to the limit cycle, like this, okay? This is called a semi-stable limit cycle, and it is an unstable type of limit cycle because there is at least one trajectory started in an infinitesimal neighborhood of that limit cycle which would diverge away from that limit cycle. That is why it is unstable. But the trajectories inside are diverging and trajectories outside are converging to the limit cycle. That is why it's called semi-stable sometimes. Okay? So the question is, can we find such a system which would give us this type of convergence or divergence? Okay? And the answer is yes. If one would like to write the system in polar coordinates, I can write just this. The rotation is clockwise, so it's going to be -1, let us say. And r dot, if I select it, it's something like this. Minus, let me say, 1 minus r squared. Okay? In that case, r equals to 1 is again a limit cycle, and there are no other periodic trajectories around it. So we see that it is an isolated periodic trajectory. So it is a limit cycle. And -1 minus r squared. If r is not equal to 1, then this is always negative, okay? Meaning that r is always going to get smaller when we are not on the limit cycle. And that means that when we are inside the limit cycle, r is still going to get smaller and smaller, okay? So this is the equations for a semi-stable limit cycle. What happens if I would like to reverse the behavior? If I want the trajectories, let us say that they're rotating counterclockwise now. Suppose that I want the trajectories to converge to the limit cycle inside, and suppose that I want the trajectories to diverge from the limit cycle outside. Write the equation of this system, okay? It's not going to be difficult. We have already done it actually. Okay? So this was an introduction to the concept of limit cycles. So in this course, we are going to see some results, some mathematical results, in order to be able to predict or rule out the existence or non-existence of limit cycles. So there are going to be 3 results that we are going to see. Sometimes these results are going to be positive results. So sometimes we will be able to predict that a nonlinear system will have a limit cycle, just as we did for such systems. But sometimes these results are going to be negative results, meaning that we will only be able to say that there exist no limit cycles for the system, and we won't be able to say if some say the same thing otherwise. So we are going to see these results starting from the next lecture. They are going to be Bendixson's theorem. They are going to be, the second one will be index theorem, and the last one is going to be Poincare-Bendixson theorem. But this is all for this lecture. We are going to see these results in the new lecture. Thanks for watching. Bye.